So when you discuss a Fourier series of a function, we normally consider a function which is defined in the interval, whose length is 2 pi. I mean, we can find the Fourier series of a function when it is defined in the interval either from 0 to 2 pi or from minus pi to pi. But now see, there are few situations where the function may be defined only in a half interval, right? See, I'm calling it as half interval because when you take, half interval in the sense it is from 0 to pi. I'm calling it as half interval because you see, when it is from 0 to 2 pi or from minus pi to pi, half of both of them is 0 comma pi. I mean, 0 comma pi is included in both the intervals. 0 to 2 pi can be divided as 0 to pi and then from pi to 2 pi. Or when it is from minus pi to pi, you can write it as minus pi to 0 and then from 0 to pi. Since 0 to pi is half of both and it is included in both the intervals, I'm just considering that half interval here, 0 to pi. So when you are given an interval, when you are given a function which is defined in the half interval from 0 to pi, or when the function is, when you are given a function whose period is pi, in such cases, see, we don't have any idea to find out the Fourier series, right? When you are given a function which is defined in a 2 pi length interval, then you know how to find the Fourier series. Then can we find the Fourier series for a function which is defined in a half interval, which is defined in the interval 0 comma pi? That's a question now, right? So to answer this question, let us recall few things first and then we'll move on to answering this question. So if you recall, when you are given a function which is defined in the interval minus pi to pi, okay, I'm just taking the full interval for convenience and then we'll move on to the other half. So when you are given a function which is defined in the interval minus pi to pi, see, we can easily find out what you call the Fourier series with this particular formula. We can write f of x as a naught by 2 plus summation a n cosine x plus b n sin x. And a naught, a n and b n, Fourier coefficients can be calculated by these three simple integrals. Okay, so this is one point which you know already. Now the question is still, I didn't forget it. The question is to find out the Fourier series in this half interval, right? So here is the question. But I'm going to use this simple idea. And there is one more thing you see, I hope you remember, which we have discussed in the last class. When you are given a function f of x, which is defined in the interval minus pi to pi, we'll try to think of whether that function f of x is either even or odd, right? So these three formulae, or else this particular Fourier series formula can be rewritten when that function is either even or odd, right? We have certain advantages when the function is either even or odd. So when you recall them again, understand 2 points. First point, the function is defined in the interval minus pi comma pi. So we have the formula which we have discussed in the last slide. Now in case when the function is even, right, when it is already defined in the interval minus pi comma pi, and now even it is even, in such a case, we know the Fourier series will get only in terms of cosine functions, right? When the function is even, we can write the Fourier series only in terms of cosine term. In the sense, you see, when you get it only in terms of cosine terms, it means the other part, coefficients of sine functions are zeros. We'll get bn as 0, right? We had seen that already. And in case when the function is an odd function, we'll get the Fourier series only in terms of sine terms. When we'll get the Fourier series like this. Correct? Now, I'm just trying to merge these ideas. The question is to find out the Fourier series in the half interval 0 comma pi. And I have certain advantages when a function is defined in the interval minus pi comma pi, and when it is either even or odd, I can easily find out the Fourier series using this formula. I'm just trying to merge these two ideas to find out the Fourier series in the interval 0 comma pi, right? In fact, you see this case, when the function is even or odd, whatever the Fourier series formula we have used, this is the basic idea to find out the Fourier series in the half interval. In fact, you see the Fourier series, whatever we are going to find out in that half interval, we call that as half range Fourier series, right? Fourier series, which you are going to find out in a half interval, right? We call it as half range Fourier series. And let us see what can we do. When you have these things, you have a question and we have an idea. The question is to find out the Fourier series in the half interval. And the idea what you have is this: when you are given a function which is defined in the interval minus pi to pi, and when it is either even or odd, we have certain advantages like this. Let me just use these two together to find out this. Now see, the question is to find out the half range series, right? Fourier series in the half interval. Let me just try to understand this by taking an example. Let us say you are given one function. Either you can take it as f of x or f of t, right? That doesn't make any difference. The independent variable may be either x or t, whatever it is. So here I'm taking it as t. Okay. Now see, you are given one function f of t, which is defined in the interval 0, pi, right? We are taking this example, in connection with the question. So the question is to find out the Fourier series, right? So I'm taking this function f of x, f of t is equal to t, which is defined in the interval 0, pi. And now my question is to find out the Fourier series of this particular function. Okay. Now see what I'm trying to do here. To find out the Fourier series expansion of this particular function, I'm just extending this function in the interval minus pi, 0. Right? The actual function you are given only in between 0 and pi. But now I'm trying to extend this function in the interval minus pi to 0, so that the new function will be either even or odd. Okay. If you recall the basic definitions, you see, when it is an even function, graph of even function is always symmetric about y-axis or else vertical axis. When it is an odd function, graph of an odd function will be symmetric about origin. I know these things, you see, we have already discussed them. So keeping those things in mind, when you know the graph of this function f of x, we can just, to get an even function. See, we have two options. You can extend it as an even function or an odd function. It's up to you. If you want to extend this as an even function, what you will do? You will just try to draw, a graph in the function in the interval minus pi to 0, so that it is symmetric about y-axis. I can just draw like something like this. Right? Now see, whatever the function you have from minus pi to pi, this whole function is even. It is even because the graph is symmetric about y-axis. So I can extend it like this. Or I want to extend it as what you call an odd function. Then what I can do? I can draw the graph of one function in minus pi to 0, so that it is symmetric about origin. So I can just draw it like this. So that now see, this function which you have defined in this interval minus pi to pi, it is an odd function. Okay, it is symmetric about the origin in the interval minus pi to pi. So like this, somehow we can extend the given function in the interval minus pi to 0, so that the new function, see, I'm taking the new function as capital F of t and the original function as small f of t, right? Whatever you are given in the question is small f of t. In fact, the question is to find out the Fourier series to small f of t. So I'm extending this function small f of t to a new function f of t, capital F of t, so that the new function is either even or odd. You can take either even function or odd function. Let us see then what happens when you take either it as even or odd. We have discussed it a few minutes ago in the previous slide. When you extend it as an even function, now what you have with you? You have a new function capital F of t, which is even, and even it is defined in the interval minus pi, pi. When you have such function, you know how to find out its Fourier series, right? To make use of that advantage, we are extending it as either even or odd. Let us see what happens actually. See, you have extended it to an f of t. So when you extend it as some function, some new function capital F of t, it looks like this. In the interval minus pi to 0, you are extending it, you see, either as an odd function or an even function. You are writing it as a new function here in the interval minus pi to 0. So that within the interval from minus pi to 0, you will get a new function like g of t. But in the other half from 0 to pi, this function must be, it is identical to the given function. Whatever the function you are given in the actual function, actual question, that function must come as capital F of t in this interval. So that's what you see in the interval from 0 to pi, both f of t and small capital F of t and small f of t, both must be identical in the interval from 0 to pi, right? when they are identical in the interval 0 comma pi, whatever the Fourier series you are going to construct for this capital F of t, whatever the Fourier series you are going to construct for this capital F of t is also identical as the Fourier series within as the Fourier series of small f of t in the interval from 0 to pi. Right? Understand? Whatever the Fourier series you are going to construct for this function f of t in the interval from minus pi to pi, right? The Fourier series expansion of capital F of t in the interval from minus pi to pi is same as the Fourier series of small f of t in the interval 0 comma pi. I'm not speaking anything else about f of t here. If we don't know anything about function f of t in the other intervals, we know about f of t only in the interval 0 comma pi, right? It may behave in any other way in the other intervals, but within the interval 0 comma pi, whatever the Fourier series you will get for capital F of t, right? Whatever the Fourier series you will get for this capital F of t, that Fourier series is valid as the Fourier series of small f of t in the interval 0 comma pi. In fact, that is where you want Fourier series expansion of small f of t in the interval 0 comma pi. Yes, you are getting it right. That's it, right? And see here, there is one simple question to understand. See, to speak out, I can extend small f of t to a capital function, capital F of t, right? To speak out, that is quite simple. But really, how can we write that new function capital F of t? When you are given the graph, for a simple graph, you can extend it, you see. Drawing a graph is probably somehow simple, but writing its equivalent mathematical expression is very difficult, you see. But how can we resolve that? See, we can. Now see, the idea is simple. You are given one function which is defined in the interval 0 comma pi, and somehow you can extend it as either an even function or an odd function. And when you extend that, you can write the Fourier series. Okay. Now, let's just think of it this way. You are trying to extend it as an even function. So as we discussed already, you can just draw a graph which is symmetric about y-axis like this. And now what happens? So you have these things. Now you have one even function, capital F of t, and it is defined in the interval minus pi comma pi. Right? When it is defined in the interval minus pi comma pi, and when it is even, we know we can find the Fourier series only with cosine terms. So we'll get it like this: a naught by 2 plus summation a n into cos nx. Right? We know it's equivalent formula for a naught and a n. If you just write them, you can write a naught as now 2 by pi into integration from 0 to pi capital F of t into dt. What is this actually? You are writing the Fourier series for capital F of t, isn't it? You're actually writing the Fourier series for the extended function. But see, in the interval 0 comma pi, look at this interesting way. In the interval 0 comma pi, whatever the function you're writing f of t and small f of t, both are identical, you know, they are same. So we can replace this function f of t by small f of t. That's one point. Secondly, even while evaluating the integrals, this 2 by pi into even the integration, you see, in the interval from 0 to pi, this function f of t can be written as small f of t. In fact, see, the definition of capital F of t itself is that capital F of t is very much similar to small f of t in the interval 0 to pi, right? So this is how you can evaluate a naught. And in a similar way, you can evaluate an. How can you evaluate an? The actual formula for an is this: 2 by pi into integration from 0 to pi capital F of t into cos nt dt. Right? We normally write it as cos nx into dx, you know. Similarly, here you can write it this way: 2 by pi into, in the interval from 0 to pi, capital F of t is nothing but small f of t. So you can write it as f of t into cos nt dt. So you can easily evaluate a naught and an. And thereby you see, when you extend the given function as an even function, you are getting the Fourier series which involves only cosine terms. Understand this point? You are given some function which is defined in the interval 0 comma pi, and you have extended that as an even function, and therefore for that even function we got the Fourier series only in cosine terms. And when you get Fourier series in cosine terms, understand this is the Fourier series in the half interval 0 comma pi. Therefore we call this as half range cosine series. because you're getting the series in cosine terms, we call it as half range cosine series. In a very similar way, you can extend that function as an odd function. When you extend that as an odd function, now you have these things. You have a new function capital F of t, which is odd, and even it is defined in the interval minus pi comma pi, right? In such a case, we'll get the Fourier series within only sine terms. So we'll get the Fourier series like this, bn into sine nx. When it is an odd function, we'll get the Fourier series only in terms of sine functions. And what is bn here? It is 2 by pi into integration from 0 to pi. We actually write capital F of t. Sorry, this is t. We actually write as capital F of t. But as we know, in the interval from 0 to pi, this capital F of t and small f of t are same. So we can replace it by capital small f of t into sine nt dt. So this is how we can write what you call, Fourier coefficient Pn. So in either ways, here in this case, when you are given the function small f of t, you have extended it as what you call an odd function, and thereby you got the series in terms of only sine functions. So hence we call now this series as half range sine series, right? Understand one simple point here. When you are given one function which is defined in the interval 0 comma pi, we have two options. We can extend it as either even function or odd function. When you can extend it as an even function, we'll get half range cosine series. In case if you can extend it as an odd function, then we can find out half range sine series. It means for one function when it is defined in the interval 0 comma pi, we have two options. We can find half range cosine series or half range sine series. For the same function, we can find either half range cosine series or half range sine series. Okay, that depends on whether you are extending it to an even function or odd function. But still the question remains, how can we extend that? Understand the idea behind this. When you are using these formulae, see, when you extend that function as what you call capital F of t, how you are rewriting it, you see, we are writing f of t as small g of t in the interval from minus pi to 0. And you're writing it as small f of t in the interval from 0 to pi. See, till now we have discussed both even functions and odd functions. But did we use this function g of t? Even in the case of even and odd functions, we never use minus pi to 0, the interval. So keeping that in mind, you see, we are simply saying it as extending it to even function or extending it to odd function. But we never use the function whatever we extend in the interval from minus pi to 0. We always use only the function which is defined in the interval 0 to pi. That's how, though we are extending that to either even function or odd function, mathematically, we never use that extended function, right? We intuitively, we just extend it, but we use the function whatever is given in the question. We use the function whatever is defined in the interval 0 comma pi, right? So keeping this in mind, you can understand when you're really solving problems, when you're working on it mathematically, we never worried about the other function whatever we get in the interval minus pi to 0. So you can simply proceed as we did in the case of even and odd functions. Keeping all these things in mind, you see, right? This is what I told you just now, half range cosine series and half range sine series. Keeping all those things in mind, you see, we can write half range sine series as well as half range cosine series for one particular function. And when you get half range sine series, you see, when the function is extended as an odd function, we'll get half range sine series. And when it is half range sine series, you see, we'll get the Fourier series in only sine terms, right? And thereby, you see, we'll write the coefficients bn as 2 by pi into integration from 0 to pi fx into sine nx. Understand the same formula you got in the case of odd functions. When you are given a function f of x as f of x in minus pi to pi, and when you write its Fourier series, when it is odd, we got the series only in terms of sine functions. In fact, the same formula here you are using, but now with this name half range sine series. The formulas are same, but the situations are different, right? Earlier, when it was odd, the function was defined in the interval minus pi to pi, but here you are given the function only in the interval 0 comma pi. Since you are given it in the interval 0 comma pi, you are calling it as half range series. And since you are getting the series in terms of sine functions here, you are calling it as half range sine series, right? And then you see, similarly, you can also write half range cosine series. And when it is a cosine series, we'll write the series only in terms of cosine terms. So that you see a naught by 2 plus summation a n cos nx, and a naught and a n can be calculated by these formulae, right? The same formula, whatever we discussed in the case of even functions, we are extending that as half range cosine series in this case, right? So that's a basic idea. And as you understood now, when you are given a function in the interval 0 comma pi, we have two options. We can find half range sine series as well as half range cosine series, right? Both the things can be found for the same function, right? Let's take this question now, and since you can understand it, get the question carefully. Find the half range cosine and sine series for the function f of x is equals to x. See, when you are given this type of question, you see, you need to observe 2 points. Point number 1, you are given the function in a half interval. See, it is defined in the interval 0 comma pi. This is your first observation. You need to always look at this. Sometimes in the question, this word half range may not be mentioned, right? You may be directly asked to find Fourier cosine series and Fourier sine series for the function in the interval 0 comma pi. So these 2 points you should observe carefully, whether the function is really defined in the half interval or not. When it is defined in the half interval, what you're asked to find, sometimes you may be asked to find only cosine series or only sine series. Of course, both also possible, right? So keeping all those things in mind, we need to take them carefully. Since here you're asked to find both cosine series as well as sine series, let me find one after the other. Let me first find half range cosine series. Right. So if you look at the formula for this cosine series, when it is half range cosine series, the series includes only cosine terms. So it is f of x is equals to a naught by 2 plus summation a n into cos nx. Right. So let me calculate a naught and a n here, where a naught is equals to, it is 2 by pi into integration from 0 to pi fx dx. Right. So then let us substitute it. It is equals to 2 by pi into integration from 0 to pi. See, the function what you are given is x, right? So I'm just substituting that x into dx. So it is equals to 2 by pi into, I'm just integrating this. You see, when you integrate x, as we know, we'll get it as x square by 2 with the limits from 0 to pi. So when you substitute the limits, it is equals to 2 by pi into, see what happens when you substitute the limits. First of all, we need to substitute the upper limit, right? So when you take x is equals to pi, we'll get it as pi square by 2 minus, when you take x is equal to 0, we'll get it as 0, right? So if you just simplify this, we'll get it as 2 by pi into pi square by 2. And here you can cancel that 2, and 1 pi can also be cancelled. So 2 and pi, when you cancel them, we'll get it as simply pi. Only pi remains here, right? So that is a naught. Now let's just calculate a n. So a n can be calculated like this, you see. 2 by pi into integration from 0 to pi fx into cos nx. So it is equals to 2 by pi, and I'm just substituting f of x. You see, integration from 0 to pi, it is x into cos nx dx. So it is equals to, see, I'm just evaluating this integral. I hope you remember, while evaluating this integral, you need to look at the integrand carefully. It is a product of two different functions, and one of them is an algebraic expression. So we can use the idea of Leibniz, isn't it? So I'm just proceeding like this, you see. I'm first of all keeping x, the first function, as it is. And then when you integrate this cos nx, integration of cos nx, I hope you remember, sin nx by n. Then minus, we need to differentiate this x, you see. Differentiation of x is 1. And when you integrate this sin nx, integration of sin nx is minus cos nx divided by n. And you see, we'll get, we have, since one more n here, we'll get this as n square. And in fact, you see, next to this, we need to differentiate 1. But as we know, the differentiation of 1 is anyway 0. I'm not writing the remaining terms. I'm stopping here, and the limits here are from 0 to pi. I hope you remember this idea while evaluating the Fourier series normally. When you have sine nx, you see, I hope you understand, you can easily understand this. When you have sine nx, while substituting the limits, see the limits are 0 and pi. When you substitute the upper limit, it becomes a sine and pi. So it is 0. And even for lower limit, when you take x is equals to 0, it becomes a sine 0, right? So even sine 0 is also 0. So for both upper limit as well as the lower limit, this term becomes simply 0. When this is absolutely 0, we can simply ignore that. That is one point. Second thing here, we have a minus sign here and there is a minus sign here also. When you multiply those two minus signs, that becomes positive. So if you just simplify this, what remains here, you see, this is 2 by pi, I'm writing it as it is, into, for both upper limit and lower limit, it is anyway 0. So I'm ignoring that. And here what remains, you see, 1 by n square into, it become positive, and now 1 by n square, I've written that. And now if you substitute the upper limit, it becomes cos n pi, cos n pi value is minus 1 to the power of n. Now see, I'm writing a minus for writing lower limit values. Minus of now lower limit. First term is already 0, I've ignored it. And here when you take x is equal to 0, it becomes only cos 0, right? Minus signs are already multiplied. So cos 0 is 1, so it is 1 by n square. You'll only get this much. Now let me write the remaining things. So we have 2 by pi is okay, and we can take n square, it is common in both the terms. So let us bring n square out of the denominator. So we'll get it as n square pi. What remains there, you see, minus 1 to the power of n minus 1. So when you get it this way, if you allow me, I'll write it here itself. So it is equals to 2 by n square pi into minus 1 to the power of n minus 1. Okay, now see, let us take two cases here. What happens to this when n is even, and what happens to that when n is odd? So an becomes, you see, when n is even, this minus 1 to the power of n becomes plus 1. When n is even, this minus 1 to the power of n becomes plus 1. So here it is plus 1 and then minus 1, cancel, and the value of an will be 0. So you can understand an is equals to 0 if n is even. Similarly, let us see what happens to this when n is odd. When n is odd, minus 1 to the power of n becomes minus 1. So it is minus 1, minus 1, minus 2. So this is minus 2 into, here is a 2 in the numerator, right? So minus 2 into that 2. It becomes minus 4 divided by n square pi. This is when n is odd. So now see, this is what you get. And now if you substitute everything into the formula, therefore the half range cosine series is f of x is equals to a naught by 2. See, we got a naught as pi. So it is pi by 2 plus summation. Look at it carefully. We need to take an. But an is 0 when n is even. So an exists only for odd values, That's why I'm taking here n is equals to 1, 3, 5, and so on. I'm taking only odd numbers. And for all these values of n, we got an as minus 4 divided by n square pi into cos nx. So this is, what you call half range cosine series. In a very similar way, we can now find half range sine series, right? We are asked to find both in the question. Now let me just extend this to half range sine series. Now let us calculate half range sine series. Okay, now see the formula. When it is half range sine series, we'll get the series only with sine terms. So we can write it as summation bn into sine nx. Right, that is the half range sine series. Now see, if you calculate the value of bn here, where bn is equals to, it is 2 by pi into integration from 0 to pi fx into sine nx. Correct? Now see, let me just calculate the value of bn here. Therefore, bn is equals to 2 by pi, integration from 0 to pi. See how much it is. I'm just substituting f of x is equals to x. So it is x into sine n x dx. So this is equals to 2 by pi into, see, keeping this x as it is, in a similar way as we did in the previous case. I'm just evaluating this integration. So first of all, I'm writing x as it is. And when you integrate sine n x, see, integration of sine n x is minus cos nx divided by n minus, when you substitute, when you integrate, when you differentiate, first of all, x, it is 1. And if you integrate minus cos nx by, you see, I'm first of all writing that minus sign as it is. And when you integrate that cos nx, integration of cos nx, as you know, it is sine nx divided by n. And already here is one more n, you see. So we get it as n square with the limits from 0 to pi. Right? Now see, we need to substitute the limits carefully. It is equals to 2 by pi into, see what happens. When you first of all substitute, one point you see, as we discussed in the previous case, when you have sine nx here, for both upper limit and as well as lower limit, the second term totally becomes 0. Right? Because of sine nx, when you take x is equal to either 0 or pi, this becomes 0. So we can simply ignore the second term here. And if you substitute the limits in the first term, when you take, here is a minus sign, I'm first of all writing minus. Then in place of x, you are substituting the upper limit pi. And there is an n square also. So I'm writing that n square. And what remains here is cos nx. In that cos nx, when you take x is equals to pi, it becomes cos n pi. When it is cos n pi, its value is minus 1 to the power of n. Then see here, this term is anyway 0. Now I'm substituting minus. You are substituting the lower limit. See, while substituting the lower limit, look at it. Here we have x. And in place of x, when you take x is equals to 0, 0 into something, it becomes completely 0 only. So therefore, we'll get simply bn is equals to minus 2 by pi into pi by n square multiplied by minus 1 to the power of n. So pi can be cancelled, Therefore, after cancelling pi, we'll get bn as minus 2 by n square into minus 1 to the power of n. If you can substitute now this in the formula finally, therefore, the half range sine series is f of x is equals to, I'm just substituting, you see, 2 by summation n is equals to 1 to infinity. I'm just substituting the value of bn. It is minus 2 by n square into minus 1 to the power of n multiplied by sine nx. Right? If you want, you can just take different values of n and rewrite it. But anyway, I'm stopping here. So this is how you can write half range cosine series as well as half range sine series for any function. Right? When it is defined in the interval 0, pi, we have two options. We can find half range cosine series and even half range sine series for the given function. Okay. One correction here. See, while substituting this, we are getting the terms only from the first one here, right? So it is not n square. This is only n. Pi by n into this. So here also we'll get as pi by n. So here also this is pi by minus 2 by n, and even in the final value, it is 2 by n. Okay, please correct it. Now let's take this question. Express the function f of x is equal to sine x as a Fourier series, Fourier cosine series in the interval 0, pi. Look at it carefully. You're asked to find, see, the word half range is not given in the question, but you're asked to see you're asked to find the Fourier series, Fourier cosine series, and that too the function is defined in the interval 0, pi. So 2 points as we discussed. When the function is defined in the half interval 0, pi, and when you are asked to find either cosine series or sine series, you can understand that is nothing but what you call half range series. Okay, so keep that in mind. And now let's see. When you are asked to find half range cosine series, with the series includes only cosine terms. So it is f of x is equal to a0 by 2 plus an cosine x. And how can we find a0? You see the same formula whatever we used earlier, 2 by pi into integration from 0 to pi fx dx. And see, I've just substituted f of x is equal to sine x here. And when you integrate this sine x, integration of sine x is minus cos x, correct? So minus cos x with the limits from 0 to pi. As you can see here, while substituting the limits, 2 by pi is written as it is. And even here is a minus sign, that minus sign, I have written it as it is. And when you substitute x is equals to pi, it becomes cos pi. And the value of cos pi, it is minus 1. Correct? Cos pi value is minus 1. And this minus is for lower limit. And here is a minus sign, that minus sign is carried as it is. And when you take x is equals to 0, it is cos 0. So the value is 1 here, cos 0. And then minus of minus, and here also it is minus of minus. So 1 plus 1, 2. So 2 into this 2 by pi, we get the value of a naught as 4 by pi. Then you see, we need to calculate an. And while calculating an, you see 2 by pi into, I've just used the same formula, whatever you use regularly, f of x into cos x. And the value of f of x, you see, it is sin x. Right? So I've just substituted f of x is equal to sin x. And now if you look at this integrand, it is just like, sin a into cos b. So you can just multiply and divide it by 2 here, so that we'll get it as 2 sin a cos b. And the formula for 2 sin a cos b, as you can see here, it is sine of a plus b plus sine of a minus b. This regular formula, trigonometric transformation, as you know. And when you compare them, actually, we'll get the value of a as x and the value of b as nx. So a is equivalent to x and the b is equivalent to nx. So when you substitute a plus b here, when you substitute a and b here in a plus b, we'll get it as actually x plus nx. Correct? X plus nx. But from them, if you take x common, we'll get it as 1 plus n into x. Right? Then similarly, here we have actually x minus nx. When you take x common from them, we'll get it as 1 minus n into x. Right? So somehow, since there is no 2 here, I've just multiplied and divided by 2. That's how I got it as a 1 by 2 here. And when you integrate this, you see, integration of sine is minus cos, right? And when you have 1 plus n into x, you see, we'll get 1 plus n in the denominator. Correct? Then when you have sine of 1 minus n into x, its integration is minus cos of 1 minus x divided by 1 minus n. And now we need to substitute the limits. And before substituting the limits, you see what I've done here. We have two minus signs, minus for this first term and minus for the second term also. When you take minus common from both, you see it comes out as minus 1 by pi. And when you substitute the limits, 1 plus n into x here, you see, if you substitute x is equals to pi, it becomes cos of 1 plus n into pi divided by 1 plus n. And here also, when you substitute x is equals to pi, we'll get it as cos of 1 minus n into pi divided by 1 minus n. Then you see, I'm taking minus. This minus is to calculate the lower limit. So minus, when you take x is equal to 0, it becomes cos 0, cos 0 value is 1. So you'll get it as 1 by 1 plus n. Then actually we have plus here because you see we already took minus out of that. Now here if you substitute x is equal to 0, even it is also cos 0, 1 and 1 divided by 1 minus n. Okay. Then you see minus 1 by 1 plus n minus 1 by 1 minus n. Then you see here, I'm just trying to write these things together. The terms involving the same denominator. Here we have 1 plus n as a denominator, and here also we have 1 plus n as a denominator. When you write those two terms together, we'll have minus 1 to the power of 1 plus n by 1 plus n. I hope you remember this value. When it is cos of 1 plus n into pi, normally when it is cos n pi, its value is minus 1 power n. And when it is minus 1 to the power of 1 plus n, when it is minus 1 to the power of 1 plus n, its value is, you see, cos of 1 plus n into pi, its value is minus 1 to the power of 1 plus n. So in a similar way, cos of 1 minus n into pi can be written as minus 1 to the power of 1 minus n. Then I'm just trying to write these two terms together by taking 1 by 1 plus n common from them. So we'll get it as minus 1 to the power of 1 plus n minus 1. And here also it is minus 1 to the power of 1 minus n minus 1. And see here one important point. When you are integrating this sine of 1 minus n, whatever the integration you got here, that is valid only when n not equals to 1. Right? What happens when n is equals to 1? You'll get a 0 in the denominator, isn't it? When you get a 0 in the denominator, you see it has no meaning. And even before that, when you take n is equals to 1 here, it becomes simply 0, sine 0, 0. So that cannot be evaluated, right? So that's how whatever you have done so far, it is true only for n not equals to 1. Right? Then see what I'm trying to do here. One point you need to just understand. While simplifying this expression, we can write it like this, minus 1 to the power of 1 plus n. We can write it as minus 1 to the power of n into minus 1 to the power of 1, which is minus 1 only. The same way here also, we can write as minus 1 to the power of minus n into minus 1 to the power of 1. So how can you write now this? It is minus 1 is only minus of minus 1 to the power of n minus 1, right? This one. Then here also we can write it as minus 1 to the power of minus n minus of minus 1 to the power of minus n minus 1. So instead of these two terms here, you see, I'm just rewriting them like this. You can see that in the next slide. See, as you can see, as how I have written them earlier, the same way we have written them as minus of minus 1 to the power of n minus 1 and minus of this minus 1. Now see, everywhere you have a minus sign, minus, minus, minus. We can take all these minus out of this so that there is a minus already outside. So it becomes plus. And then you see, we will get it like minus 1 to the power of n plus 1. And here also it is minus 1 to the power of n plus 1. Now we are just taking two different cases, when n is even and when n is odd. When n is even, we'll get minus 1 to the power of n as plus 1. So if you just simplify them, even minus 1 to the power of minus n is also plus 1 only. So when you simplify that, you see, and even after taking LCM, of course, we'll get the value of an. You can just cross check this. You will get the value of an as 4 by 1 minus n square into pi. In a similar way, when you take n as odd, see, you will get that minus 1 to the power of n as minus 1. So in either case, when it is minus 1, you see, we'll get the value of an as 0. And as we discussed already, that is true only when n is not equals to 1. And in particular, when you take n is equals to 1, see, a1 becomes f of x into cos x. F of x is sin x now. So I've substituted that, and we can write, you see, if you take 2 inside, we can write it as sin 2x. I mean, 2 sin x cos x is sin 2x. So when you integrate this sin 2x and simplify this, see, we'll get the value of a1 as 0. You can just cross check this. And the value of a in either case, whether n equals to 1 or n not equals to 1, you see, we got it as simply 0. That's how you see the Fourier series, I mean, half range cosine series. I've just substituted the values of a naught and an. An exists only in the case of even functions. I mean, even values of n. That's how, see, we get the Fourier cosine series like this, right? So for this particular function sin x, we can find the Fourier cosine series like this. Okay.